Yeah, good morning. In this session, I would like to demonstrate a material balance problem involving recycle. You might have solved many such problems in your first course of chemical engineering, material and energy balances. Please try to look at what you are doing when you are solving such problems analytically, and or in case if you want to solve the problem by using a process simulator like Aspen. For example, if you try to look at this problem, feed gas consisting of hydrogen, nitrogen and argon, which is an inert material, is mixed with recycled gas and enters into a reactor where 10% of nitrogen as per this stoichiometry. Ammonia is completely separated from the unconverted gases. So in order to avoid the buildup of inerts, 5% is purged, and based on 100 moles per hour of fresh feed, calculate the recycle rate, composition, product rate and purge rate. As you can see, because we are interested only in mass balance, uh, though the temperature and pressure are not given for the feed gas, whatever values that you assume are not going to actually affect the result of mass balance. Now let us see how this can be simulated using Aspen. So the first step is define all the components that you have in your product: nitrogen, hydrogen, and then ammonia. So once we have these details, then we will be able to, as we have seen, it is only a mass balance problem. So whatever is the property method should not be affecting your mass balance calculations. So having selected the property model, you can go to the next step, that is simulation environment. And as you can see, various models that you have, because the fresh feed is going to be mixed with the recycle, so I have a mixer, and this is followed by a reactor. Now you don't know the kinetics, only conversion is known. So the only option for us to use is a stoichiometric reactor. Given the conversion, we'll be able to perform the mass balance. And in the same way, we were given that the product that got formed, which is ammonia, is completely separated from the unconverted gases, unconverted reactants. So such 100% separation without going into the design aspects can be achieved by using a simple separator. Then the exit, the bottom probably can be complete ammonia, and the exit is going to contain unreacted nitrogen, hydrogen and also argon. So to avoid the buildup of these inerts, we are going to use a splitter, which is going to take some amount of purge. So part 5% is taken as purge and remaining 95% is recycled back. So let us try to provide the input and output connectivities to this problem. Click on the material streams. So we have fresh feed. Then the combined feed is entering into a reactor. The reactor exit is going into a separator where ammonia is completely removed, let us say from the bottom product, which is the product of this particular process, and the unconverted gases are sent into this splitter. Out of this, 5% is taken as purge and the remaining is sent back and mixed with the fresh feed to give you the recycle. Let me slightly name some of these. This is your product stream. This is your purge. This is your recycle. And this is your fresh feed. Now, once again, before going into the other details, if you take some kind of a envelope across all these blocks, now what are the streams that are entering into this feed? So this has to be specified, and along with this, we may have to specify the block details, operating conditions, and so on. So given this information, because all these models are going to work in rating mode, we will be in a position to calculate the purge product and also all the other intermediate streams. So let us go into the next step to provide the necessary input. Now you can see it is asking information about the feed stream and some information about the blocks, different blocks. So as I said, you can assume any temperature and pressure because it is not going to influence your result. And the flow rate is per hour of product. So it has moles per hour. And the composition is already given to you in terms of mole fractions. Hydrogen, I think, is 75.16. Hydrogen is 75.16, 24.57, and 0.27. So let us provide this detail. 0.2457 and 0.27% of argon. So 0.0027. So the total is becoming 1. Sorry, not this. Argon. Hydrogen, this is 0.2457. 0027. Yeah. So having defined the feed stream, now you can go to the next input screen. So we are going to define the stoichiometric reactor, the temperature and pressure. Again, this doesn't matter. So let me assume the same conditions. Go to the next step. So the reactions, we need to define the stoichiometry of the chemical reaction. So nitrogen, the coefficient is 1, and hydrogen, the coefficient is 3. N2 plus 3H2 giving rise to 2NH3. And the product is ammonia, which is 2. And we were given that the conversion is 0.1, 10% with respect to. So we have specified this. Now go to the next step. That means the reactor block has been completed. The next one is the split fraction. So you can see the product stream should contain only ammonia. So the separator is able to have 100% separation, which may not be possible in real practice. So try to be careful. So we wanted to remove all the ammonia that is coming into this split, into this separator should be sent into the product, but it should not allow any of the other components into this stream. So in other words, this split fraction works like this. Whatever ammonia that is entering into that separator, all that should come into the product stream. But none of these, nitrogen, hydrogen, argon, can be sent into this product stream. Automatically, because of mass balance, ammonia will be coming into the bottom and all the other components will go into the vapor product. So next. So this is the splitter. We already know the purge is going to be 5%. So out of the inlet, 5% of the inlet is sent into the purge and remaining 95% goes into the product, into the recycle stream. So we can see that the required input is complete. So we should be in a position to solve the problem. Now try to be careful in analyzing this problem. Probably we have not come to this type of calculations. First of all, why there were iterative solutions? Do you think you will so many iterations, about 20 iterations to solve this problem if you are solving this analytically? No. No iterative process is required if you want to solve this problem analytically. Now what is the order in which these computations are going to be done? P1, which is a mixer, followed by reactor, then separator, then splitter, and once again this process is iterated over 20 times. Why this is so? You can see in the beginning. So method has been suggested as Weijstein, and the convergence streams, the tear stream has been taken as recycle. Why this is required? Now the computational order has been decided by the simulator, Now this can be done by assuming or by considering a particular stream as the tail stream. Suppose if you want to start your calculations with B1, which is a mixer, we know the feed stream, but do we have any idea about the recycle stream? We don't know what is going to be the recycle stream. So what the simulator does is, having decided this as the tail stream, so it guesses values for this recycle stream. What do you mean by guessing values for the recycle stream? If there are C components, at least you need to guess values for C plus 2 variables. So here you can see that there are 3 components, nitrogen, hydrogen and argon. So at least 5 variables need to be assumed. So assuming certain values for this recycle, now we will be in a position to solve mixer model to calculate the outlet. We know the input to the reactor model along with its equipment parameters and operating conditions. We should be able to solve this model to calculate stream 3. And again, once we know the input, we will be able to calculate the product stream and stream 5 by solving this model. And similarly, once we know the input, we will be in a position to calculate purge and recycle. Remember, we started with an initial approximation for about 5 variables. We were able to get an updated set of values for the recycle stream. Check whether you have come to a convergent solution. Otherwise, a new recycle value is taken and the process is iterated, right? So with this background, you can see from the control panel, maximum number of variables that did not reach convergence happen to be 5 because there are 3 components, 5 variables are involved. So probably we will see what Aspen does in order to guess these values. So as you go on progressing, you can see that 5 variables did not converge, 5 variables, 4 variables, 4 variables. And as you approach the solution, now only 2 variables did not come to a convergence. That means out of the 5, even if one variable is not able to match with the previous set of values as per your tolerance, you need to proceed with one more iteration till you are successful with respect to all the variables. All the variables need to come to a convergent solution. So in the case of design spec, we were having only one manipulated variable. Whereas in the case of recycle, we have several variables depending on the number of components involved in the recycle. So as we progress with these calculations, you can see after 20 iterations, we were able to come to a convergent solution. It seems to be a burden of solving such problems involving recycles using a simulator when compared to the analytical approach. However, you can make any small modification and you will be able to get your results quickly once you have such a simulation model. Now you can look at the results. Probably I'll show you one by one. Now what is that you are interested in calculating? We wanted to calculate the recycle flow rate and its composition. Now you know what is the flow rate of this recycle. So if we have given in terms of moles per hour, so let me convert that into moles per hour. So you are putting in only 100 moles per hour of fresh feed, but the recycle is having about 612. So what is the recycle ratio? R by F, 612 by 100, almost 6 times. Now you can see what is happening to the composition of this recycle stream. So this is the composition of the recycle stream. Similarly, the same thing, you can find out what is the purge rate. Probably I'll just show you these results. So you can see the purge is about 32, something like that, in terms of moles per hour. So about 32 moles. This is the recycle, and this is the total amount of flow that is going into the splitter. Out of this, 5% is sent into the purge. Remaining 95% is going here. Now you can see all the streams across the splitter will have the same state, like temperature, pressure and composition will remain the same. So out of the given calculations, we have calculated the recycle rate and its composition, purge rate, and similarly we will also be able to identify what is the product rate. So we were able to produce the product ammonia at the rate of about 33 moles per hour. Right? So this way, you could see how the mass balance problems can be solved involving recycles. If possible, we will try to discuss certain theoretical aspects maybe in another session. Now, do you think this is the only possibility? Is there any other possibility apart from taking the recycle as the tear stream? For example, is it possible for me to take stream 2 as the tear stream? In case if I have selected stream 2 as the tear stream, I will not be able to solve the calculation starting from B1, right? So because stream 2 is guessed, I will be able to solve this reactor model to calculate stream 3, then calculate product on stream 5, then calculate per jet recycle. Once you know recycle, because feed is given, I will be able to solve this model to calculate 2. We started with an initial approximation and we got an update. In the same way, you will be able to convince yourself that it is possible to solve this problem by considering stream 2, stream 3, stream 5 or even recycle as the tear stream. But depending on what tear stream that you have considered, the computational sequence will change. If you take recycle as the tear stream, B1, B2, this is the order in which these blocks must be solved. If you start with stream 2 as the tear stream, then B2, B3, B4, B1. This is the order in which you have to solve the problem. If you start with stream 3 as the tear stream, then B3, B4, B1, B2. This is the order in which the computations have to be done. So even for this small problem, first of all, unless and otherwise you decide on the type of tear stream, you will not be in a position to identify the computational sequence. In fact, there are a number of algorithms to decide on the tear stream, and even after deciding the tear stream, then only you will be in a position to calculate the computational sequence. So with this background, I would like to now, for example, once you have this flow sheet, though it is possible to solve this model analytically quite easily compared to this effort, now you would be able to identify what will happen if I change the purge rate, what will happen if I try to change the conversion, what will happen if there is some other change with respect to the separation. All such analysis can be done quite easily. When you want to repeatedly solve this problem for different set of inputs, that's where the simulation model will be handy. If you want to solve this problem only once, solve it by hand. So with these comments, I would like to close my session.